So I guess I'll introduce the next speaker. It'll be Eric Nielsen from New Mexico State, right? And Eric has worked in direct imaging for many years. So this is the last of the planet detection methods. I guess we didn't invite the pulsar timing people this time, maybe next time. And direct imaging, near and dear to my heart, and I think its glory days are still ahead of us. So please take it away.
All right. Thank you, Tim, for the introduction. So yeah, indeed going to talk about direct imaging here. What we can do with the technique, how it works, what the limitations are, how we use it for demographics. And rather than building up to it, I'm just going to skip straight to the end. So here are actual images of extrasolar planets orbiting the nearby star HR 8799. 1, 2, 3, 4 planets orbiting that star there. Wonderful orbit movie from Jason Wang. Actual data, you're looking at actual light from the star, from the star and from the planets as the planets go about their orbits over a decade. And we've seen versions of this plot a few times already this week. Shout out to the NASA Exoplanet Archive for these amazing data visualization tools. And just to sort of orient ourselves, going to throw up some of the solar system planets here, Earth, Jupiter, and Saturn. And the direct imaging population lives out here, these yellow dots here. So you can see that these are things that are more massive than Jupiter, further out than 5, 10 AU. And so we're going to talk a little bit about why these objects are out here, why these are sort of the sweet spot for modern direct imaging, what it takes to go to other types of planets. And just to answer the question up front, why are these planets the ones that we can see with direct imaging? These are the ones we're not quite these ones are the ones we're not quite able to get with direct imaging yet. And at the risk of oversimplifying, planets are faint, stars are bright, and planets are right up next to the star. I'm contractually obligated to give you this analogy here. It's like looking directly into the beam of a lighthouse and trying to spot a firefly sitting at the edge of the lamp. The numbers actually just about work. A firefly is about 1/1,000,000th the brightness of a lighthouse lamp, which is about what we can do from the ground with direct imaging now. Okay, so to make sure we're on the same page, direct imaging from the ground is going after self-luminous planets. So we're not talking about reflected light. We'll talk more about going after planets in reflected visible light on Friday. But for now, direct imaging is based off of thermal emission, going after the thermal emission, usually in the near infrared or mid infrared of these planets that are self-luminous. And so we're not thinking about, for the most part, reprocessed starlights. So your intuition is good here. The planets are going to be easier to detect if they're further away from the star, and a brighter planet is going to be easier to detect than a fainter planet. So let's define a few terms. I'm going to start out with this term you hear in direct imaging a lot, contrast. Contrast is just the flux of the planet divided by the flux of the star. This is going to be a quantity that depends on wavelength. Planets are not the same brightness at all wavelengths. Stars are not the same brightness at all wavelengths. A wavelength dependent quantity. Just to sort of tell us where we're aiming for here, if you think about Earth in reflected visible light, Earth has a contrast with the sun somewhere around 10 to the minus 10, 1 part in 10 billion, billion with a B. So that's a really, really tough contrast to get to. And we'll hear on Friday the technological challenge that is and how to overcome that. But we're going to try and look for more favorable contrast ratios to actually image planets with today's technology. And the most basic thing is find brighter planets. Can we find a planet that's brighter than Earth is in reflected light? And what works out really well is young giant planets. Young giant planets are still hot and bright from their initial formation, and therefore they have a more favorable contrast ratio with their star. You can think of this as terms of conservation of energy. All the material that made up a planet was initially spread out in the protoplanetary disk. It comes together to form the planet. It loses gravitational potential energy. As it loses that gravitational potential energy, that energy has to go somewhere. It goes into heating up the planet. Planet starts out hot and then cools down, gets fainter over millions, billions of years. So if we can go after a planet when it's only a few 100 million years old or less, we have a much better chance of actually seeing light from that planet. Just to add a few numbers here, here's great evolutionary models from Adam Burrows. Looking at stars in blue, brown dwarfs in green, planets in red as these objects cool over time. So they all initially follow the same basic path. They start out cooling and contracting. See if I can get that. Cooling and contracting over their first few million years. A star will eventually ignite nuclear fusion in the core, fusing hydrogen. It will stop changing luminosity. This is luminosity on the y-axis, time on the x-axis there. Brown dwarfs. Brown dwarfs are going to have little blips of nuclear burning. They're going to fuse deuterium. They're going to fuse lithium, the more massive brown dwarfs. But they'll eventually run out of those, and they'll continue to contract and get fainter and fainter and fainter throughout their lives. Planets, not even going to do any deuterium burning, just going to get fainter and fainter over their lifetime. And so if you want to have a chance of detecting a planet when it's still bright, you're going to have to go after the younger planets, the younger stars hosting the younger planets. So things that are 100 million years, 10 million years, or younger. So early success with direct imaging technique. This object, 2MASS 1207. 2MASS 1207 is the host star. It's not even a star. It is a brown dwarf. It is a 25 Jupiter mass brown dwarf, companion about a 5 Jupiter mass planetary object here. You can ask the IAU whether or not this counts as a planet or not. But this is a nice sort of planetary mass thing. Let's leave it at that. So the contrast ratio, because again, the primary is a brown dwarf, is very favorable, somewhere around 1%, 0.5% in the H band, 1.6 microns, closer to 3% in the L band, about 3 microns. And so you see that, contrast depends on wavelength. And you want to start thinking about where is most of the emission coming out. Stars are not black bodies, planets are not black bodies, but if you have in your head the picture of a black body, you're not that far off. So you want to sort of chase where the peak of the emission is to have the most favorable contrast, the peak of the emission for the planet. In a little more detail, here is a plot of contrast. So contrast with a sun-like star on the y-axis versus wavelength going into the infrared here on the x-axis. And so as you go to a very, very hot object, the contrast in the near infrared, in the H band and the K band, and the contrast in the mid infrared, the L and the M band, are not too dissimilar. So you have similar contrasts, similar ease of detection, no matter what band you're at. But as you go down this plot, as you go to cooler and cooler objects that are either older or lower mass, these objects are going to have the contrast in the H and K is going to essentially drop off a cliff, whereas the L and M contrast, the mid-infrared, is not so bad. So I'm going to leave this as sort of a spoiler for the end of my talk. Gee, wouldn't it be nice if we had some sort of 6-meter space telescope optimized for mid-infrared observations? Come back to that in a few slides. Okay, so that's point one, contrast. You're looking for something that's very faint next to something that's very, very bright. Point two is angular resolution. You want to be able to see something that's really, really close to the star. Most exoplanets are less than 1 arcsecond away from their star. The usual analogy I like is if you take a coin out of your pocket, hold that coin 1 mile away, the width of that coin is 1 arcsecond. So that's a really small angle on the sky that we're talking about between the star and the planet. So it's a faint thing, very, very close to the bright thing. And just to add some numbers here, imagine you're an alien astronomer 10 parsecs away from the solar system, looking back towards the sun. Earth would be 0.1 arcseconds away from the sun, Saturn would be 1 arcsecond away. So most exoplanets, not all of them, but most exoplanets, as seen from Earth, are 1 arcsecond or less from their star. Think back to introductory astronomy. If you want to improve the angular resolution, you either need to increase the diameter of your primary mirror, or you need to go to shorter wavelengths. And here we hit a contradiction. We know that if we want to chase the emission, if we want to go after better contrast with the planet, we want to go to longer and longer wavelengths. But if we want better resolution, we kind of want to go to shorter and shorter wavelengths. And so we're going to have to figure out how to balance these to really optimize this and give us the best chance of finding planets. One more number that you'll see thrown around here is what's called the inner working angle, or IWA. Inner working angle is basically just the minimum separation at which you can reach some particular target contrast. Okay, related to improving angular resolution is adaptive optics. When light goes through Earth's atmosphere, the wavefront of light gets distorted, and adaptive optics uses a mirror that can change shape, a deformable mirror, to correct all the horrible things the atmosphere is doing to your light, bring you back to more or less diffraction-limited image. A AO system today will run somewhere around thousands or many thousands of times per second, changing the shape of that mirror to correct for what the atmosphere is doing to your wavefront. It's one of my favorite AO examples here. Everyone make a mental guess of what astronomical object we're looking at. This is from the 3-meter Lick telescope with no adaptive optics correction, so there's just natural seeing. You've all made your guess. If you guess the planet Neptune, you are correct. That is the exact same telescope, exact same wavelength, exact same object. Just now, adaptive optics has been turned on, and you see the much higher detail on the surface of the planet there. So again, really getting back to higher resolution by having that adaptive optic system on. One more technological innovation here is the idea of a chronograph. A chronograph is going to block out the light from your star, allow you to see the much fainter planet next to it. So it gets a little bit more complicated when you think about wave optics. Light is a wave. Light will diffract around any hard edge. So clever chronograph design to both reduce diffraction and also to block out as much starlight as possible, allow you to see the much fainter planet. Okay, so suppose you've done all that. Suppose you've taken all my advice. You've gone after young stars. You gone to the biggest telescope you can find. You have a great adaptive optic system. You have a great chronograph. You're all set, ready to find planets. You take an image with, say, the Keck telescope of a young star. You subtract off the smooth part of your PSF, of your point spread function, and this horrifying thing is what awaits you. This image just completely filled with speckles. Speckle, 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 all over that image there. And these are, in many cases brighter than planets, in some cases about the same flux as planets. They're all over your image. They change over time. They have timescales of minutes to hours. If they had timescales of less than a second, like atmospheric effects, that'll be fine. Those would just average out over an hour. If they had timescales of weeks, that'd be fine too. Just calibrate them out over the course of a couple nights. But no, they have some sort of timescales sort of on your observing timescale. And so these things are there all over the image and changing on a really inconvenient timescale. What are they? They are imperfections in your telescope. Your telescope optics are not perfect. Your mirror is not the perfect smooth shape you might want it to be. All of these imperfections put some of the starlight in a different part of the image than you'd otherwise like it to be. So the starlight goes to the bad place, you end up with speckles all over the image, and those imperfections in the optics change over time. The temperature of your telescope changes over the course of the night. As your telescope tracks across the sky, gravity's pointing in a different direction, and you have these imperfections changing, and so the speckle pattern changes minute to minute to minute, hour to hour to hour. You have to somehow get past these speckles in order to see the planets that are hiding underneath. And the trick that has worked the best for this is called differential imaging. Basically a way of subtracting off the PSF, the point spread function of the star, to get to the planet and the faint things underneath. To oversimplify it a bit, the way that differential imaging works is you have two images, one that has the star and the planet, one that only has the star. You subtract those two images from each other, and you should be left with just the planet. So you see the difficulty right away. How do you get yourself an image of the star without the planet in order to make this subtraction work? Didier Close showed a really nice disk image of Beta Pictoris on the first day of this conference. That wonderful disk image came through this wonderful trick of differential imaging. So different flavors of differential imaging. I'm going to go through three of them. One of them is called spectral differential imaging, or SDI. The idea is you find some sort of spectral feature that your planet will have, hopefully where there's more flux in one wavelength than another, and you hope that your star has a different spectral signature, and you use that to essentially have an image where the planet is gone. So as an example, this is the SDI instrument at VLT. You have one filter at 1.6 microns. The planet should be relatively bright there. But if the planet has methane, it's going to absorb, that the planet's atmosphere will absorb a lot of light at 1.63 microns. And so you have one narrowband filter where the planet is bright, one narrowband filter where the planet's essentially faint. The star is about the same brightness in both those filters, and you have what you wanted. You have two images now, one of star plus planet, one of only star. You can subtract them and see the planet hiding underneath. This works really well, not just with narrowband filters, but with integral field spectrographs. I'll get to those a little bit later on in the talk. But you can think of an integral field spectrograph as taking a series of images at slightly different wavelengths. And this little movie is stepping through those wavelengths. And as it steps through wavelength and increasing wavelength, you see the speckle pattern here slowly, slowly moving out, going to larger and larger separations. Speckles are a diffraction effect. Speckles live in lambda over d space. If you increase the wavelength, if you increase lambda, the speckles are going to move further and further away from the star. And you see two things in this image that are not moving. That thing there and that thing at the top. Those are the actual real objects. Those are not created by diffraction, and so they don't move when you increase wavelength. And so spectral differential imaging, SDI, one way to get rid of the speckles and be left with the real object. Another flavor of differential imaging, reference differential imaging, or RDI. Essentially, you look at two stars. One star has a planet, one star doesn't. You hope you're not so phenomenally unlucky that both stars have a planet in the exact same location, and you just subtract those two images. You hope the two speckle patterns are more or less the same. In more modern terms, you do this in a little bit more complicated way. You make a giant PSF library of star after star after star, do a linear combination of all these images in your library to subtract off the speckle pattern. You hope that the speckle pattern has some sort of modes the telescope goes through that repeat on some sort of regular basis. And the type of differential imaging that's been most successful is this thing called angular differential imaging, or ADI. If you have an alt-az telescope, and most modern telescopes are alt-az telescopes, as that telescope tracks a star from the east, high in the sky, into the west, that telescope is going to be rotating as it follows the star across the sky. Most instruments will have what's called a derotator. You literally just rotate the instrument in the opposite direction so that your field stays fixed, so you can take long exposure images without everything blurring out. The genius of ADI is literally just turn that derotator off. Don't have a derotator. Just let your image rotate over the course of the night. Anything real, a planet, a binary star, a disk, anything real in that image is going to rotate from minute to minute to minute as you track that field across the sky. But speckles are not created in the sky, they are created in your instrument. They're created by your telescope, they're created by your instrument, and so they will stay fixed. So here's a nice summary movie of that happening from Christian Marois. This is Keck data of HR8799. So you see the raw 10-second integrations there. The smooth part of the PSF has been extracted off. You see the horrifying speckles. But if you look at the compass rose there, you see the compass rose is rotating from image to image to image. The speckles, they stay fixed. They're not moving. They're created by your instrument. But the real things, like the planet here, is rotating as the telescope rotates. So real things rotate, fake things like speckles just stay fixed. You can then median combine all your images, get a beautiful image of the PSF, subtract it from the individual images, and you see two of the outer planets popping out once that's done. And then these are all 10-second integrations, so just stack them together, median combine, and you see a even closer planet that becomes visible as you stack more images together. And so ADI was the powerful technique that led to the discovery of HR8799, led to being able to continue to follow the orbits over decades here. Again, I'm favorite movie of all time, so I'm just going to stare transfixed for a little while here. Just this really great seeing the planet's orbits going about, obeying Kepler's laws over the course of more than a decade. So these planets here, they're between about 5 and 7 times the mass of Jupiter. Inner one's about 15 AU, outer one's about 70. A young star as promised, somewhere around 40 million years. And it's worth pausing here to say, where did that mass come from? Masses are not a thing you measure directly with direct imaging. How do you get the mass? Well, you turn to your favorite evolutionary models. So you have light from the planet, so you can get a sense of what its luminosity is. So if you think the luminosity of the planet is this, the question becomes how massive it is. Well, in order to answer that question, you're going to have to know the age of the star, age of the planet. If you think you're looking at a 1 million year old star, great, you discovered a 1 Jupiter mass planet. If you think that star is a good deal older, around 200 million years, that's not a 1 Jupiter mass planet anymore. It's 13 Jupiter masses, the canonical planet brown dwarf boundary. Or if it's closer to 8 billion years old, it's something around a 73 Jupiter mass brown dwarf. So mass depends on age. So you need to get the age of the system in order to have a model-dependent mass that you can now assign to the object you just found. So how do you get ages? Well, here's a little gallery of some directly imaged planets. My slide only has so much space, so I apologize if your favorite directly imaged planet is not in this gallery. But you can divide them up by what sort of stars they're orbiting. And most of the stars are either in moving groups or young associations. Not a coincidence, young stars near the sun tend to be with the other stars they formed with. A handful are orbiting field stars, but mainly young moving groups, young associations. So I'm just going to leave this sort of reference up here. If you want to get the age of a given star, first, check if it's a moving group. Banyan and lacewing are nice ways to calculate the probability of your star being in any given moving group. If it's a field star, you still have hope. You can get a rotation period from TESS and use something like gyro interp or star dates to get an age posterior out of that. If you have lithium or calcium, Baffles is really good. If you have lithium, Eagles is really good. So lots of different packages to get yourself an age posterior for the star that you think you have a planet around. Okay, so let's talk a little bit about setting the stage for demographics. We want to think about how do you get demographics out of your direct imaging survey. And sort of the core sensitivity of a given direct imaging observation is a contrast curve. Contrast curve is flux ratio, delta magnitude as a function of separation from the star, separation in arc seconds. And contrast curves, they come in all different types, but they all have the same general shape. Less sensitive close to the star, more sensitive as you move further and further away. Stars are bright, so the further away you get from that bright star, the more sensitive you're going to be. The exact shape, the delta magnitude you get to is going to depend on the telescope, the instrument, the wavelength you're working on, how you're reducing the data, brightness of the star. All these things go into figuring out what the actual contrast curve is going to be. And let's just build a little intuition here. So we can think a little bit about how these contrast curves scale with stellar properties, for example. So here's a contrast curve. I chose one of my favorites from the Gemini Planet Imager. So this is a contrast curve in separation versus delta H. Get to a delta H of about 15 magnitudes or 10 to the minus 6 at about half an arc second. And then we want to move that from observer units into physical units. So we want to move it over to Jupiter masses and physical separation in AU. Well, we know the distance, so we can do that. The distance change pretty easily. We can turn to our favorite theoretical models and the age of the star in order to turn that into mass. And so that contrast curve ends up looking like this for a G0 star at 20 parsecs, 100 million years, hitting somewhere around 4 Jupiter masses at 10 AU from the star. If I take that hypothetical star, still leave it as a G0, still keep it at 100 million years, but I start moving it either closer or further away from us. If I move that star closer to us, contrast curve moves over to the left there, and now we can get that 4 Jupiter mass planet at only like 2 or 3 AU, whereas if that star is 150 parsecs away, I can only get that 4 Jupiter mass planets all the way out here somewhere around 70 AU. So closer stars are going to be better in order to find closer planets. If now I change the spectral type of the star, I go from an A0 to an M3. Earlier type stars are intrinsically brighter, and so the contrast ratio is less favorable to me. So I can only get higher mass planets that are bright enough to be seen below the noise of my instruments. But if I turn down the brightness of the star, go all the way down to M3, I can start reaching 1 or 2 Jupiter mass planets with that same contrast curve. But most important of all is age of the star. So again, leaving it as G0 star, leaving it at 20 parsecs. And now I'm just going to change the age of that star for the same contrast curve here. If it's a 10 million year old star, I start hitting 1 Jupiter mass planets. I actually hit the edge of my evolutionary model grid there. And as I go to older and older stars, I become less and less sensitive to low mass planets until by the time I get to a gigayear or so, I'm essentially not sensitive to planets at all. I can only see brown dwarfs. And so with direct imaging as it exists from the ground right now, we really need these younger stars to go after the younger planets. So we're going to talk a little bit about one instrument in particular. I'm obviously very biased. I'm going to talk about the Gemini Planet Imager, instrument I've worked pretty heavily with here. But other instruments have similar features, but slight differences between them. So GPI, Gemini Planet Imager, installed a Gemini South in 2014. This is it being lowered into the attached to the telescope. Gemini is an 8-meter telescope. Gemini South in Chile here. And so, as the name implies, the Gemini Planet Imager, GPI's, role in life is to image planets. So high order AO system, 2 deformable mirrors, chronograph using ADI and SDI, integral field spectrograph. And a common theme of direct imaging is these are not one-person instruments. This is this sort of thing requires very large teams to make them happen. GPI had over 100 scientists and engineers coming together to design the instrument, to build it, to test it, to commission it, to design the survey, to run the survey, to reduce the data. So huge thank you to the entire GPI team, without which none of what I'm showing would be possible. Okay, what does GPI data actually look like? So here is GPI data, raw GPI data, just straight from the detector of the planet Neptune. And what you see is just a weirdly pixelated image of Neptune. If you zoom in and zoom in again, every single one of those pixels is a spectrum. Every single pixel on the surface of the planet Neptune there is a spectrum, 17 elements all across H-band. And so basically anything in the image, you get a spectrum of for free. Low resolution, so R of 50, but a spectrum nonetheless. And so you can think of an integral field spectrograph one of 2 ways. It makes a spectrum at every single image, a spectrum at every single pixel, or it makes a series of images at a series of slightly different wavelength slices. GPI's first big success was finding a planet around the star 51 Eridani. Here's a nice artist conception of that planet. But of course, with direct imaging, you don't need artist conception. You can just look at the actual planet. So here's the actual discovery image here. Again, integral field spectrograph. So we're stepping through wavelengths across the H-band. Always look for the little arrow pointing to this little dot here. And you'll see that as we step through wavelength, going to redder and redder wavelengths, the dot appears out of the noise and then fades back in. Brighter at some wavelengths, fainter at others. What this is telling us is that this planet has a lot of water and methane in the atmosphere, a T spectral type here. So water and methane absorb light at these wavelengths, absorb light at these wavelengths. Light can only escape the planet in between, which is why we get that sort of peak of emission in the middle of the H-band there. GPI allows us to take spectra at multiple wavelengths, so Y, J, H, and K, as well as L and M from Keck, in order to actually constrain the shape of the spectrum at different wavelengths. And spectra are important. Direct imaging is one of the few techniques that allow you to actually take a spectrum of the planet you're trying to study. So with a spectra, you can learn about the atmosphere, you can learn about the temperature, the luminosity, the abundances, the weather, you can learn about clouds on the planet. So all sorts of things that are possible once you have actual light from the planet. You can do orbits. Another excuse to show more orbit movies here. So, if you're patient and you keep observing a planet, you'll see it move over the course of, several years over its orbits. These are 2 planets in the same moving group. So they're both 24 million years old, both 10-ish AU away from their star, very different masses, 2 Jupiter masses for 51 Eridani b, 12 Jupiter masses for Beta Pic b. And the thing you are all doing right now by looking at that screen is you're doing orbit fits by eye. You can immediately tell which one is the more edge-on orbit and which one has the more face-on orbits. Don't even need MCMC. You can just really just look at that, watch the planet move, and get a sense of that orbital motion, even though for neither of these do you see a full orbital arc. All right. One last plug to Jason Wang's orbit movies, just incredible astronomy visualization here. But yeah, if you have a little bit of patience, you can watch these planets move. You can learn about their orbital properties. You can get the 7 major axes of the orbit, the period, the eccentricity, the inclination angle. Learn all these things with enough orbital motion. Don't even need a full orbit. You just have to have good enough observations, enough precision to see that orbital motion over time. One thing I didn't list, though, was planet mass. With imaging alone, you are not going to get planet mass. I'll talk about this in a few slides, but if you combine imaging with other techniques, you can get yourself mass. But if all you have is imaging, you're going to need something like an evolutionary model and an age and your favorite, as well as the planet brightness, in order to get a model-dependent mass for your planets. Tim showed these as well, so I'm just going to plug them one more time here. If you have some orbits you'd like to fit using direct imaging data, either by itself or with other data types, Orbitize or Vara, Octofitter, really nice packages to get yourself at a good orbit. Oop. All right. I got so eager, I actually opened up the Octofitter page. All right. And now I'm doomed.
Keynote. Run this. Did you? Okay, let's ask. The presentation should still be open, right?
Okay. So you're going to hear more about giant planet demographics tomorrow from Brendan Bowler. So I'm not going to go really deeply into demographics here. I really broke things, didn't I?
Stop sharing for now. Yeah, I don't know. It's just really odd. The Finder.
Well, the good news is we got through all the orbit movies first.
Fix it. Let me see. Yeah, it just disappeared. Keynote. There we go. It's back, right?
Hey, wonderful. Thank you.
But on Zoom might not be, right? Can you see it on Zoom? Sorry. Yeah. Okay. Fixed it for a second.
Okay.
It's not. Okay. We do share. Hang on for a second, and then we'll do this. And I think we're back.
Wonderful. Thank you so much. All right. Ooh, okay. Gave you all time to think about orbits. Pushing forward here, beyond orbits, you can also think about demographics. So again, Brendan Bowler is going to talk about this in a lot more detail, but I am just constitutionally incapable of giving a talk without a tongue plot in it. So here's a tongue plot. This is the GPI's 300-star survey tongue plot, semi-major axis on the x-axis, planet mass on the y-axis, giant planets at the bottom, brown dwarfs at the top, red dots show detections, colors and contours show the sensitivity of the survey to different types of planets and brown dwarfs. And one of the many reasons I love tongue plot so much is you can read the occurrence rate, read the demographics right off this plot. Look at the 160-star contour. It goes for brown dwarf masses from about 10 to 100 AU. There are 3 brown dwarfs inside that contour, so the occurrence rate is 3 out of 160, or about 2%. 2% of stars hosting a brown dwarf between about 10 and 100 AU. If you want more fancier calculations of demographics than that, check out this paper or come talk to me after the talk. All right. So in the last couple of minutes, I'm just going to do a very quick lightning round run through of some of the big results from direct imaging over the last several years. Come talk to me about any of these afterwards if you want to hear more about them. Planets and disks. We see disks in direct imaging. With apologies to the Blues Brothers, we have both kinds of disks. Circumstellar, protoplanetary disks and debris disks, and we see planets in both of them. And so we learn about planet-disk interactions using direct imaging. We can couple direct imaging with high-resolution spectroscopy. Instead of R of 50, much better, R of 30,000, R of 100,000, really high-resolution spectra, instruments like CRI-RES and KPIC. So getting to this very high resolution for, first of all, better atmosphere studies, but also giving you the possibility to get radial velocities of the planet. There was the question yesterday about whether you can do radial velocities of brown dwarfs. I'll do you one better, radial velocities of planets, looking for exomoons. So this is a potential technique to get at exomoons by using the direct imaging / radial velocity technique to see if the planet is going back and forth due to a moon orbiting it. Interferometry. You can combine direct imaging with interferometry here. LBTI, if you have 2 large telescopes, do a lot of work. You can interfere the light between them. So LBTI did this wonderful host survey looking for extra zodiacal light. Very recently, last few years, VLTI gravity has come online, and Tim mentioned gravity before. It's a phenomenal instrument, just incredible sensitivity, getting very, very close to the star. This is the detection of not beta pic B, which I was showing before, but beta pic C, which is 3 times closer to the star. Really need an instrument like gravity to actually detect something like that. This is an actual spectrum, medium resolution spectrum of the planet Beta Pictoris C. One of the things I love most of all about gravity is just how hard it makes it for authors to make their plots, because in order to show how small the gravity error bars are, you need to have these sort of subpanels there. That top panel is my favorite of all. In 2 days, the planet moved enough to be detectable in orbital motion. So just amazing relative sensitivity of gravity there. Tim gave a great introduction to this, so I can skip over how you use astrometry to find potential planets. This has worked to great effect for planets like AF-LEP-B, found by 3 teams simultaneously. All 3 papers were on archive within 24 hours of each other, as well as other planets and brown dwarfs found via this method. So if you combine astrometry and direct imaging, you get the mass from astrometry, you get all the benefits of direct imaging, so you get the mass and the atmospheric properties. Works very well combining radial velocity and direct imaging too. Tim mentioned this planet as well, Epsilon Indi AB, triple system, K-star, 2 brown dwarfs, and a planet orbiting the K-star. Normally in these sorts of plots from direct imaging, there'll be a little arrow to tell you what little blob you should be looking at. Don't need that there. It's the really, really bright thing at the top with an airy ring. That's the planet. If anything, you need help figuring out where the star is. It's that little orange star symbol in the center, because it's been so effectively removed by PSF subtraction. And this really shows the power of James Webb, because going after a planet that's really much, much older than most of the planets I've been talking about. So the field is changing so fast that the things I told you at the start of this talk are no longer true. I told you that planets are usually found around 100 million year old stars or less. The star is the age of the solar system, about 5 giga-years old, and yet there's that planet being able to be seen in the mid-infrared because James Webb has this extraordinary sensitivity at these longer wavelengths where most of the planet light is coming out. And one more James Webb result, sort of hot off the presses here. Last couple of weeks, detection of a planet around the star TWA7 by Anne-Marie Lagrange using James Webb data. This is less than a Jupiter mass, 1/3 of a Jupiter mass, 1 Saturn mass, so really getting to much lower masses than have been possible in the past. Again, the power of going into the mid-infrared. Very quick advertisement for the future of direct imaging. You're going to hear a lot more about this on Friday about the Habitable Worlds Observatory, which will make the leap from self-luminous planets in the infrared to reflected visible light. Actually going after Earth-like planets, the leap all the way to the 10 to the minus 10 contrast. You need to actually see Earth-like planets around nearby stars, characterize their atmosphere, learn about whether they have biosignatures or not. And I'm just going to rush through this, but some further reading on direct imaging, a lot of great review articles in the literature that you can look to. And I'm completely run out of time, so I'm just going to throw up my conclusions and take any questions you may have. Thank you.
Thank you. Please come to the front for questions. I'll ask one online. I'll distill 2 questions into one. 2 ways you mentioned to get masses: 1 from a stellar age in the model, 2 from astrometry and orbit fitting. What typical precisions can you hope to get in both cases on the mass?
Yeah, excellent question. So I left you with the sort of observer-centric view that we're in this horrible position of having to trust the theorists, having to trust the modelers in terms of the masses we can get. The good news, I want to make sure I hand it to the theorists here. The modelers' masses have been very, very accurate. Now that we're starting to get dynamical masses by combining direct imaging and radial velocity, direct imaging and astrometry, the predictions from the models, these models that we've all been using for decades now, turn out to be pretty accurate. And so it seems like we can really trust these model masses for all the objects we've tested so far. But we're going to keep testing more and more masses. The second question for astrometry for radial velocity, it's going to depend a lot on how much of the orbit you've seen, how much of the how much of the orbit you've seen, and the accuracy of the astrometry or the radial velocity. I want to say the latest mass for AFLEP is 3.5 plus or minus 0.5.
3.75 plus or minus 0.5. And maybe it'll be useful to just drop a number of references in the chat so we can do that.
Perfect. Thank you.
Yes. Please.
Hi, Eric. Is this one, first of all? Oh, yeah, we're good. Cool. Hi, Eric. I do have a question, which is that I know that recently there's been a lot of work in the machine learning community with regards to signal processing and image processing. Do you expect that to be at some point implemented into direct imaging, and that can help you get to even fainter planets?
Yeah, so question about signal processing. There have been lots and lots of attempts to use various types of machine learning to do better than the human eye. As of now, the human eye is still unparalleled. Most of the automated reduction pipelines still come down to a human has to actually look at those and say, no, 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 yes, maybe, no. I'm bad at predicting the future, so I won't try. But as of now, human eye has still been pretty good.
Sorry, I guess the question was more about like tamping down the noise in the image versus like actually picking out a planet.
Okay, yeah. So it turns out that actual analytical math has been the best answer there. Basically you find the linear combination of modes that best fits the noise in your image, and that's really had the most success in getting rid of basically the entire speckle pattern.
Fantastic. Thank you.
Thanks. I'll do another one online. Any words about the Roman coronographic mission?
Ooh, okay. You're going to hear a lot more about the Roman chronographic mission from Vanessa Bailey on Friday. But yeah, Roman and HWO are both going to move towards reflected light planets. So in the case of Roman, it's going to be reflected light Jupiter-sized planets and a couple AU. In the case of HWO, it's going to be Earth-like planets. But yeah, there's basically a really big gap you have to overcome, sort of contrast from the ground that you could hit right now, somewhere around 1 part in a million, 10 to the minus 6. To get to reflected light, you need another 3 orders of magnitude, 10 to the minus 9. And Roman's going to be the great test case showing us how we can actually do that.
Thank you. So please come on Friday if that is your question. And please go ahead.
Thank you for the presentation. I wonder, is it possible to determine radius of a planet through direct imaging, especially super Earth or potentially habitable planet size radius through direct imaging?
So yes, with current direct imaging, since we're looking at self-luminous planets, there are a lot of degeneracies in terms of how hot the planet is, what its luminosity is, what its radius is. You can get model-dependent radii, but there's a question of how well constrained those currently are. When you do reflected light, there's still going to be degeneracy between phase function and albedo and radius, but you have the radius is a lot more well connected to your observables in that case, and so I think things are pretty promising there. That if you see reflected light and you have several observations, you can probably nail down the radius pretty well.
Okay, I think we're right on time. There are a couple more questions in the chat, but I think we can answer those in the chat. So we'll take a break, and what are we back at 10:30? Thank you.